we go.
Okay. Thank you for having me here today. My name is Ken Levenson. I'm an architect with over 20 years of experience and a certified passive house consultant. And our company, 475, was just founded in the last year, dealing with high-performance construction issues. And so I would like to give a brief introduction to our company and what we're about, and then we'll launch into our presentation, which is about foam-free, high-performance building enclosures and how to go about making them. So up front, our company is a place where the blower door is king, and all the passive house people can very much appreciate this, as air tightness, air control is really a dominant issue in building performance. It's also a place where foam is not the solution, and we're actually looking at building solutions that allow one to not use foam, and that is what we were most interested in optimizing, and we'll get into all of that briefly. Our company is a place where passive house is part of the solution. Of course, we'd love to see all buildings being built to passive house standards. We know that's not realistic at the moment, although we do push in that direction. We see passive house as a North Star guiding star, and so that all projects can be tighter, can be more higher performing, and we see it as a clear distinction and definition of high performance. Our name is actually derived from the passive house standard, 4.75 kilobTUs per square foot per year as the annual heating demand for passive house construction. Our company was actually born out of a passive house project. It was a gut renovation of a historic townhouse in Brooklyn Heights, New York, where I was the architect. The builder was another partner, Sam McAfee, and the building science consultant that has helped us with the blower door tests and some of the issues regarding detailing was a building science consultant and architecturally trained in the Netherlands, Floris Keverling Boesman. We were able to hit 1 ACH 50 on this house, but it was a very difficult process. And while the results are quite pleasing aesthetically and environmentally, it's performing very well, we're happy to report. We realized the materials and the knowledge in the building supply industry in the U.S. was not readily available, nor were they much interested regarding trying to get to passive house level performance. And so the three of us decided to set off and see what we could do about rectifying the situation. And this brought us to an older place than Brooklyn Heights, Schweizingen, Germany, which is the home of Proclima. And Proclima is a national leader in Germany as well as a European leader, and by default a worldwide leader in air sealing, air control, vapor control systems. We were very happy to have a relationship with Proclima. We are the exclusive importer and distributor across the U.S. for these products. And we're also very happy to report that just this spring, the Proclima product line won the Best in Test for airtight systems. And this was in a publication that is the equivalent of the Consumer Reports for Germany. And we're very happy that in a place where the product quality is very high to begin with and the competition is stiff, that Proclima is the best in test. And how we do this and how what is so special about Proclima and what we're trying to do with these air sealing vapor control systems is that it's really a complete A to Z approach to air sealing and vapor control. And so we have membranes, gaskets, tapes, adhesives, accessories that deal with interior air tightness and vapor control as well as the exterior. And so you have a complete approach to the building. Our company is founded in an e-commerce model so that we are able to sell coast to coast from the get-go. Anyone can go on, click, order products, and have them shipped directly to your job sites or wherever you would like them. We also have a growing amount of building science-related information and other items that we feel useful to high-performance builders, architects, designers. We're also very happy to be hosting Passive Passion documentary, a 20-minute documentary by Charlie Hoxie that is the only place you can see it without paying because we are paying for the privilege on the web. And so we encourage everyone who might be interested to take a look on our website. And our website, we're continually updating with new details, new information. We have a blog where we regularly post informative short articles on different aspects of building science and how we can better optimize our construction. So we encourage you to take a look there. Also, we're regularly tweeting, joining the conversation around building issues, and encourage everyone to join the Twitter conversation with us. So in our short lifespan, we're very fortunate to have projects, incorporating our projects and demonstrating the potential of what we're going to be talking about here, from Maine to New York, Wisconsin, Seattle, and to Alaska. So we're really coast to coast distributing these products. With airtightness and vapor control as the primary focus of the company, we also do carry some complementary products such as a ventilation system. We're not competing in the central ventilation systems, but we do make a supply a very special decentralized high efficiency heat exchange ventilator. It's also made in Germany, in Berlin. It's over 90% efficient, very quiet, and you install these little machines in pairs, where in a small apartment, let's say, you would put one of these fan heat exchange units through the wall in a bedroom and one in the living room, and they cycle back and forth in 70-second intervals, one supplying while the other's exhausting. As the air is exhausted, it transfers heat to the ceramic core, the waffle-like thing you see in the middle, and then after 70 seconds, when the fan reverses, the supplying air picks up the heat that's in the core and is transferred back, maintaining near consistent temperatures inside and outside, while giving continuous fresh air ventilation. So for retrofits or homes where a centralized system may not be appropriate, or in additions to existing homes, this can be an ideal solution. Things like hotels, apartment buildings as well. And we have a triple pane skylight. And for the skylight, we concentrate on the skylight because while there are many window manufacturers from Europe and high performance being developed and available here, skylights seem to be sorely lacking. And we don't want to have these be compromised holes in our otherwise robust enclosure. And so these skylights factored from Poland, triple glazed, triple gasketed, and help maintain the consistency of interior environmental comfort. And finally, we have thermal break material for cantilevered concrete construction, high-rise construction. And we're continually looking now to see what specialty products we may be able to bring to the market to complement and really bridge what people's aspirations are towards high performance to help them make it a reality. So the presentation at hand, foam-free high-performance building enclosures. We have a few learning objectives here. One, we want to talk about what are the goals of high-performance enclosures and how those goals are evolving, and really how they're changing today is a big deal in what is happening. We want to understand foam in this context, a little bit about the history, and we want to talk a little bit about how foam is, as these high-performance goals are evolving, foam is falling short in some important ways, and we want to understand how to practically construct high-performance enclosures that are foam-free. So here we go. So we're going to want to briefly touch base on qualities of high-performance enclosures. So the industry standard qualities for high performance and for any kind of minimal performance, I guess we should say, water control, number one. We need to keep the rain out. No matter what we say or do from here forward in the presentation or in our buildings, the job number one is that the enclosure needs to shed water properly. The sills need to work. The gutters need to work. The roofing, the siding, everything needs to shed. If you're not shedding the water properly, sort of all else is lost. Then next, air control is second in importance, and then we have vapor control and thermal control, and these are the four primary control items that, as defined by the Building Science Corporation in their order of importance. Cost control and we would say predictability and durability are always an issue, and certainly if you're calling something high performance, should be included in that. Now, today we find ourselves in an interesting situation where, because of evolving sort of a combination of societal inclination, whether it's regarding green or sustainability or comfort or durability, along with increase in tandem with that, increasing code requirements, increasing business awareness, industry awareness, but also with the introduction of the Passive House Standard to the United States, a real clear sort of leap in expectation is being brought to bear. And so we have emerging qualities that in some cases are re-emerging for some people because a lot of what we're trying to do today are things that have been lost in the past. So today, greater air control, more resilient vapor control. Our thermal control goes to thermal bridge free. We want greater cost control. We want to introduce that we want to be more sustainable and green. We want to address the climate crisis we face. I would say we also want to be able to confidently install and work and produce high-performance buildings in cold and wet and difficult weather and situations, that these materials cannot be so delicate that we can't push around the clock and around the calendar as business today dictates. More predictable and durable. So some of these are just upping the ante. So I just want to touch base super briefly on the history of foam, just as coming out of 1839, discovered by apothecary, polystyrene that is, not foam per se. Polyurethane in 1937, which is the basis of most foam. And then really so in World War II it was used in U-boats for flotation, it was used in aviation, other mechanical production. It was really the 1950s so much. The big chemical giants really took it on and developed it and brought it to market for commercial roofing, packaging, and other items. In the 60s, on-site spray application was developed, the mechanisms, the technology for it. And in the 1990s, we really see these companies pushing with a rapid rise in the residential building application. And today, in terms of high-performance construction, and high-performance construction is still a relatively small part of the overall industry, but within the high-performance realm, really foam has become the dominant piece of vocabulary in the high-performance conversation, and most conversations begin and end talking about foam. And so we're here to sort of rethink that a little bit, because we think that foam is part of our optimistic technological future, human progress, and really goes in line with the ideas of the space age, and it parallels it very well, the development of nuclear energy, processed food, and pharmaceuticals. Like some of these things, while they may be great in many ways, there are reasons to question them and to question the ubiquity of them and reliance on them, and that maybe there are things that we can be doing preemptively that can negate the need for them and we can have healthier, longer-lasting buildings without it. So, like Dustin Hoffman in The Graduate, he may be questioning the great advice that plastics is the future. So, while that's sort of a high-level point to make possibly, let's dig down a little bit more and why foam-free. And I guess this is another high-level statement, but we want to build foam-free because we can build better without it. And we can meet these emerging demands for no additional cost. And so we want to go through what these emerging demands are, how things are changing, and how we can do it well, and how, in some respects, foam is not living up to the requirements of these emerging demands. So air control has been in a continual progression of having a tighter requirement. So historically, in high performance, 3.0 ACH 50 has been the benchmark. It had been since revised some years ago to 1.5 ACH 50. The science behind this isn't so important as the magnitude is and the idea of it. The passive houses come in then and sort of reset the conversation and the context of the conversation, saying that really to be a passive house building, the requirement for a new building is 0.6 ACH 50, more than halving again. And what a lot of people don't realize is that while the requirement is 0.6, that's just, the minimum to get certified. The goal is actually 0.3. So that's a 10 times, a factor of 10 difference between what we've historically been calling airtight and what our goal for airtightness is. And again, whether that goal is practical on any given project is up for debate, but as a North Star and as what we're trying to go toward, it's a very real and useful number in our opinion. And so when you're talking with people about airtightness, we need to be clear what we mean by airtight, because one person's airtightness is another person's very leaky building. And as we get tighter, foam gets less effective as an airtight air control layer. And we'll look at that. Another reason why airtightness is second only to water control, and the blower door is king, as we say, is that it disproportionately affects very important things in the building's functioning. Indoor air quality, the fundamental idea that you cannot control the quality of the air until you control the air itself. And so airtightness is critical in that. Comfort, drafts are uncomfortable. It's as simple as that. Heat loss, thermal bypass. So even if you have a well-insulated building on the face of it, if we have a leaky well-insulated building, it could perform as much as 5 times worse than a well-insulated tight building, an airtight building. So that is a huge difference in thermal performance. And thermal bypass plays a hand in that. We'll talk about that in 1 second. Finally, air-transported wetting is a bigger liability than diffusion wetting. So while, of course, we must keep the rain out and need to shed water properly, air leaks and air can carry a great deal of water vapor with it. To the right is the iconic building science diagram showing a sheet of gypboard where moisture has diffused through the gypboard over the course of a heating season, depositing 1/3 of a quart of water over that time. But given some air leakage, that air transport can carry as much as 30 quarts of water in that heating season. So we have just a drastic geometric difference in exponential difference in what the wetting is possible. Thermal bypass, once more, has a huge influence on the effectiveness in the insulation, and thermal bypass can take on many different directions and characteristics, as we see by these fundamental diagrams. And thermal bypass can even be a huge issue in foam-based enclosures. So here we have the iconic photograph from Building Science Corporation of Joe Stiebrick's barn showing the foam panels shrunken and the discoloration due to thermal bypass. So we need to be very careful of airtightness, even in spray foamed or board foamed or SIP panel buildings. So Joe says this past summer at the Building Science Camp, saying that air sealing both sides of the wall is more important than the fluffing of the insulation in the cavity. So with these words, it's more important than ever, or we understand how important it is to make airtight inboard and outboard of the insulation. Here we have two construction types that we're showing. One is an I-joist with sheathing on the left, and on the right is a double wall stud, and we'll be looking at these details a little bit more closely later on. But the idea is that we have an airtight layer on both sides, inboard and outboard of the insulation, and it should be top and bottom. We want to have, and side to side, basically the insulation surrounded on all 6 sides by air tightness, and thereby negating issues of thermal bypass and optimizing the insulation, as well as optimizing our approach to issues such as draft control, energy efficiency, and preventing wetting of the enclosure. So with air tightness objectives, it's important to take a look at what materials are up to the job. So here we have a list of materials that aren't necessarily authoritative in their description, but it gives sort of a relative value, and what we're asking folks to do is to take a careful look at what materials they're depending on to create their air control layers and think about, really, are they up to the job? And so we go from one extreme where on the right, you know, cellulose, dense packed cellulose, we love dense packed cellulose. It's a wonderful thing, and we'll talk about it more. All buildings should be built with it is sort of our blanket oversimplified statement, but it is not an air control layer. It is not airtight. Foam is, for many reasons that we'll see, is really not ultimately a good airtight layer. It might be, but by the conservative estimation is that it is not. The same with traditional weather-resistant barriers. Then we have layers in the middle that might be, they might not be. Concrete, foam as well, plastic sheets, they might deteriorate. And then we have on the left materials that certainly should be, but then we also want to be careful with them as well. Plywood should be OSB, may depend on the thickness. Concrete will be, but we don't like to depend on it because of the cracks that may happen, and how thick the concrete is in relation to that. So the durability over the time of the building. And then we have new generations of house wraps. We have pressure-sensitive acrylic adhesives, EPDM rubber gaskets, butyl tapes, and so forth. So this is just to throw the conversation out there. So one example of this is the traditional weather-resistant barrier, the traditional house wrap, as defined by ASTM standards and the U.S. Industry. Puts their tightness at 0.004 CFM per square foot, and I believe that's at 75 pascals. This is not airtight. It's not going to get us to the airtightness that we need given everything else and the complexities of the construction. And so while the traditional house wraps are called non-perforated, they actually have micropores. And they have the micropores to deal with vapor transmission, but it's working against us in airtightness. The new generation of weather-resistant barriers have a factor of 100 times more airtight, and they actually bring airtightness to bear in a house wrap. So vastly different, same description, generic description, but vastly different performance. So airtightness should be the top priority to ensure health, comfort, a robust structure, and energy efficiency. Second only to water. And hand in hand with water, which by we mean bulk water, rain, and so forth, we want active vapor control. And why this is emerging and evolving requirement is that too often now and in the past it's really been a passive vapor control methodology, and we'll look at that in a little bit here. But what we want an active vapor control, because assemblies dry through vapor diffusion. They may get wet in any number of ways, but they dry through diffusion. So we want to maximize the drying potential of our assemblies, and this means allowing to dry to the inside and the outside. Obviously we want to minimize wetting, and we also want to help the drying by managing the moisture in the enclosure. And it's important to note this quote on the right, that you need to assume that the building will get wet somehow at some point in time. Stuff happens. So you need a moisture-tolerant design. You know, the water is going to get in no matter how well we build these buildings. There are going to be little leaks here and there. It's not going to be perfect, and we need to assume that moisture is getting in. It happens all too often. So the goal of vapor control is to have the drying capacity be greater than the moisture stress on the assembly. And if we do that, we achieve freedom from damage. So if we're drying through vapor diffusion, it's important to understand first the vapor direction of that is being applied to the assembly. And that means in cold and mixed climate zones, it's principally the vapor direction is to the outside. Meaning there's lower vapor pressure on the outside, higher on the inside, and it's pushing, wanting to push through from the higher to lower. In the hot and humid climate zones, and where you have central AC running virtually all year round, the vapor drive direction is in the opposite direction to the inside. So if we're in a cold mixed climate, for example, you want, as the vapor wants to dry to the outside, and we want to encourage drying through diffusion, we should have a vapor open assembly to the outside, allowing it to dry. On the inside, where the vapor is principally coming from, we may want to have retarding, and we may want to have vapor variable retarding, depending on the situation in the assembly. And a basic measure of that is a 5-to-1 perm ratio rule of thumb. So if you have 5 perms on the outside, you want no more than 1 perm on the inside, just as a round number. And so this always advantages the drying to the outside, which is the way the vapor wants to go, encouraging drying. In a hot and humid climate, it's essentially reverse, where you're looking at vapor retarding on the outside and being vapor open on the inside. So if we take a look at the exterior parts of the enclosure, the roof and the walls, and we want to be vapor open, ideally this means a vented roof. And ideally this means a membrane that is vapor open and that also serves as the air tightness layer as well. So here we can see project in Maine underway, where we have weather-resistant barrier over the trusses without any sheathing between it and the truss. Over that is laid battens, and then we have a vented roof that's being attached to the battens. So we have a vented roof over vapor-open material, allowing maximum drying to the outside. A similar situation on the walls. You may or may not have sheathing on the walls, but we want to have it be as vapor open as possible once again. And here we have the weather-resistant barrier with battens and a vented wall, vented siding, encouraging the drying to the outside, maximizing the drying potential. Sounding a little bit like a broken record, but it is so important. We feel that we're working with the physics of the water, the moisture, and helping it along and not against it. In this, what we were just looking at is this house wrap and this new house wrap. While we talked about the air tightness before, what's interesting about the vapor control is that the traditional weather-resistant barrier has no active vapor transmission, and so it requires greater vapor pressure to work. And the vapor literally has to push through the pores in the membrane, and if you have significant wetting at once, it's essentially clogs up and is less permeable ultimately than the new generation weather-resistant wall barrier that is technically at a lower perm rating, but because it actively transports water on a molecular chain, it consistently will move the vapor through the membrane to the outside, even under very low pressure differences, maintaining the maximum drying potential. So we've talked about having a vapor open roof assembly, a vapor open wall assembly, and then what happens all too often in traditional construction scenarios is then we take all the seams, and particularly the flashings around the windows, and we apply a vapor barrier. And this is particularly bewildering because around a window installation or door installation is the place where condensation is most likely to take place, where leaks are most likely to happen. So this is the maximum potential for wetting, and we're placing a dam between the wetting and the outside. It wants to dry to the outside in the direction of the vapor drive, and we're stopping it. So it's just going to sit there until something not too good happens to the house. So rather than damming the vapor from drying, preventing it from drying at the most critical junctures, the new approach is to use tapes and materials that complement the vapor openness of the wall and roof and are vapor open, so that where you have moisture, the possibility of moisture around the window installations, the door installation, you have a vapor open membrane that allows it to dry out. So again, working with the natural forces, not against them. So, and then there's foam. And what has been the traditional approach to high performance building, we sort of see on the right in this diagram from the Building Science Corporation, who I have to say we admire the Building Science Corporation directly. We refer to them all the time, use all their books. There's just such a wealth of information. And all we're, in our own little way, we're trying to help engage the conversation and push everything along. So using their diagram, we're showing a relative humidity of 50% on the inside at 70 degrees Fahrenheit. In the wall assembly, then, the dew point is at 50 degrees. And while things are not going to condense in the middle of the wall at the dew point, the first condensing surface, which is typically the back of the exterior sheathing, is where it will condense. And so the typical answer for avoiding moisture problems has been how much insulation do we need to add to the outside? And that has been shortened over time to just say how much foam do we need to add to the outside, as foam has sort of become the go-to product. And so by raising the temperature, by adding foam, however much you calculate is needed, to raise the temperature of the interior side of the exterior sheathing above the dew point, which is at 50 degrees Fahrenheit at this point, then you're preventing condensation from happening from the vapor diffusion and air transported wetting. But what we have is something that is trying to prevent wetting from happening, yes, but it is not helping us dry. It is a passive and sort of prophylactic approach to the problem of moisture in the assembly. The foam is essentially intolerant. That if we have these incidental leaks, particularly at windowsills and whatnot, and the water needs to get out, we want to encourage it to get out to the outside, and all too often foam is effectively semi-impermeable or impermeable, and the water is sitting there and causing problems. So let's take a closer look at component vapor impermeability in regards to this. So aluminum foil faced foam is impermeable. XPS is semi-impermeable. Even EPS, which can be semi-permeable, if you get to a thickness which often is needed in these cases, it's impermeable, semi-impermeable, 3 inches of unfaced EPS. And so it's putting the brakes on drying when we want to be accelerating the drying in complete sort of going in the opposite direction of where we want to be. Too often, roofing is a vapor barrier, or a special case where often where you have an asphalt roof and you have a vapor barrier, we want to be very careful not to put another vapor barrier under it, because while a vapor barrier under it may prevent diffusion wetting from the inside, if there is any incidental wetting over time from one source or another, you have a threat of creating a bathtub of sorts. And wetting can come from a number of ways, including from bypass through masonry walls, etc. So it's a very complicated thing, but fundamentally, given one vapor barrier on the outside, we basically say we never want to have two vapor barriers in the construction. So with the foam, drying and managing the moisture, another issue is that we want to be picking materials that help us manage the moisture and manage and encourage the drying. Again, assuming we're incidentally getting wet, foam and water want nothing to do with each other. Foam doesn't help water. Water wants nothing to do with foam. Once the water's into the enclosure, the foam is not helping you. So we say, why not pick a material that is actually going to work with you, work with moisture? Dense packed cellulose is such a material which is hygroscopic, and where you get wetting in one part, it's going to actively move the moisture to a drier area and allow the and encourage the moisture to dry to the exterior. So if we have a vapor open outside, wall and roof, preferably both vented. But you could have an asphalt roof, and we'll speak to that in a minute. If we have dense packed cellulose in the wall, which helps manage the water and doesn't ignore it the way foam does, we want to look at the interior vapor control. And here we have some typical options. Because we do in the colder climates, it is good to have some vapor retardation, and we also would like to have some vapor variability possibly. So plywood and OSB and paper-based membranes do this. Felt does it as well. Natural materials I should say, in natural materials that when they're dry, they are less vapor open. And as they get wet, they become more vapor permeable. So you just want to look at the assembly you're putting together. You want to determine, based on the ratios, based on what's being put together, what might be the most appropriate. And whether it's plywood, OSB, a paper-based membrane, or an intelligent membrane, which has an even greater permeability curve, which we'll speak to in a moment, one thing would be very nice is that the vapor control layer on the inside is also the air barrier. Again, on the inside of the insulation, air barrier, vapor control, optimizing the insulation between. Now, where we may think an intelligent membrane might be useful, just briefly to show the curve of the humidity, showing the relative humidity along the bottom and the perms along the side. We see in the wintertime it's virtually vapor impermeable, and as the humidity grows around it, its vapor profile opens up and allows drying. So what this really is about is that, particularly at a roof situation, and let's say you had an asphalt vapor impermeable roof, where the vapor drive in the winter is out on the left, the intelligent membrane effectively acting as that vapor barrier that we want in the winter keeps the moisture from diffusing into the enclosure. Yet in the summertime, when the vapor drive is reversing direction, and we don't want the vapor barrier on the roof, and this is where we really get into trouble, because if we had two vapor barriers year-round, in the summer, the intelligent membrane becomes vapor open and actually allows drying to the interior. And so what we have is a way to minimize wetting in the winter and maximize drying in the summer, sort of giving you the best of both worlds. So with air and vapor under control, next is the thermal insulation. And obviously we want to be foam-free with that as well. So looking at two wall sections, one for new construction, one for retrofit, we look to build thermal bridge-free continuous insulation on the new with the double stud wall construction on the left. And on the right, we're showing a traditional construction with continuous rock wool insulation on the outside of the sheathing. And typically you would see foam there, but again the foam is acting as a vapor retarder, or vapor has a much higher vapor impermeability. With the rock wool, we are vapor open. Now the R value of rock wool is substantially less than the polyiso or EPS that you may be putting on the wall, but we feel the vapor openness is that important, and coupled with air tightness, with a wind-tight, airtight, weather-resistant barrier on top of the rock wall, you're getting overall a higher performing enclosure, a more robust, longer-lasting enclosure that's not going to have rotting problems down the road. So this is basically the the two diagrammatic ideas of thermal bridge, free continuous insulation without foam. Cost control, I just want to simply say that we believe while costs vary from region to region, contractor to contractor, project to project, there are a lot of complexities in determining what the ultimate cost of something is. But if the systems are optimized and you're looking at this thing holistically, you should be able to build better than foam for less than foam. You should not be spending more to get away from foam. In fact, we really believe that you should be able to save money. In terms of sustainability, the toxicity of spray foam cannot be understated. I mean, this is a real toxic sort of cocktail of chemicals. You know, it would basically equate it with giving your house chemotherapy, and you know, it just why would this be our first choice in addressing sustainability and energy efficiency? The global warming potential. Spray foam is a disaster. It's you know, if you have a 100-year payback for an insulation product, we are not addressing the climate crisis. We have a couple of decades at most to get serious about it. And if we're installing things in the name of energy efficiency that won't realize any positive impact, only negative impact on our climate global warming issues for 100 years, the game is lost, in our opinion. So we really want to look to insulation materials that have very low global warming potential, if not negative. You know, and of course, dense packed cellulose is practically zero, if not negative. You know, some of the other foams, the board foams and whatnot, they've pushed down the global warming potential significantly. But in comparison to dense packed cellulose, again, I mean, they're just many multiples higher, if not infinitely more, if cellulose is really down at zero. So I think this is a serious consideration to make in what we're doing. This is not theoretical. We have a time limit on what we're doing here. And so we think we should act accordingly to that. So we also have, while we're environmentally conscious and trying to deal with the climate crisis, we have crazy 24/7, 365 days a year lives. It seems more now than ever. And we need to be able to work and push projects forward and not compromise the quality of what's getting done and the robustness of it. Unfortunately today, spray foams and butyl-based adhesives and what makes up the most traditional aspects of high-performance building components have relatively high temperature requirements, and they have relatively low moisture requirements. And of course, spray foam needs to be very clean to be done properly, and so forth. And so we're relying on materials that, if we're to really optimize their use, you know, work has to be put on hold, has to be delayed, and so forth. What we're excited about is with some of the new materials and the new capabilities of them, you can actually work down to 15 degrees. And we've had a project in Duluth, Minnesota, where it was tapes were being applied down at 5 degrees and seemed to be working very well. And they're also, but 15 degree is the recommended limit there, but that's really get you through the bulk of the year, moist without artificial heating or any of that nonsense. And we're also, the products are more moisture tolerant. You know, job sites are wet, either from the construction itself or from the weather. And to have products that are more moisture tolerant and still be able to execute at the desired level is really a sea change. So with this is really, what does this is the pressure sensitive solid acrylic adhesives. It's really a molecular bond. There's no solvents, and it allows it to work in much more difficult conditions. Excuse me. So maintaining that bond. I should say pressure-sensitive acrylic adhesives has come out of the aeronautics industry, and it's actually used on flaps on the wings where, as the plane's coming in to slow down and the flaps pop up, there are actually flaps in there in the thick of the battle, if you will, that are attached with metal flaps that are attached with nothing more than, quote-unquote, nothing more than these pressure-sensitive acrylic adhesives. So they're standing the test of time and in unbelievable sort of work conditions. So to achieve true air, vapor, and thermal control, it must be predictable and durable. So this is ultimately the true test, right? I mean, we could have sort of the most beautiful drawings and the most beautiful job site, but at the end of the day, if it's not predictable and durable, we really don't have high performance. And so key to predictability and durability are unbroken control layers and protected control layers. So this includes things like continuity, particularly penetrations being addressed, flexible connections, sequencing of work, and simplifying the work. And we want to protect control layers with exterior vented rain screens and roofs and interior service cavities. So to briefly look at this, in the context of foam, you know, it's really, and particularly as these standards are getting tougher, foam is being shown to not be optimally predictable nor durable. For one, like spray foam is not continuous. We're going from stud to stud, plate to header. It doesn't necessarily expand in the directions desired. The quality control is difficult. I mean, it can be well done. There's no doubt about it, the quality control, but we're talking about on-site manufacturing of highly sensitive and toxic chemical components. I mean, we're basically taking a pharmacy. Some of these components need to be treated better than pharmaceuticals, and we're moving to the job site and asking contractors to act in a manufacturing capacity that I don't know that we asked anybody else to do, and I think as a result, you know, we're having wide-ranging results on the site, and too often, you know, we're having problems, which we'll take a look at in a moment. I would say, you know, one of the biggest things in terms of approaching this in terms of a passive house perspective and high-performance perspective is that in testing, the leaks, given particularly spray foam, but also board foam, are not readily identifiable or repairable. If you're looking up at a ceiling of 8-inch spray foam and you're seeing a leak come out somewhere, it's kind of like looking at the ceiling, you know, gypsum wallboard ceiling and trying to pick from that leak where in the roof it may be leaking. You know, you could end up to actually get to it having to tear out a ton of foam. And we, you know what the chances of that are of happening. So because it's not readily identifiable in the testing or so easily repairable necessarily, it's a big issue in our opinion in terms of ensuring robustness. Also, just back to the particular nature of the spray foam and its delicateness, if you will. If the substrate's too wet, if the substrate's too cold, if the substrate's too dirty, if we have off-ratio spraying, or if we have too much sprayed. All these different things will contribute in different ways to foam not being optimally placed or failing outright. You know, we know of many stories, and we talk to spray foam installers who are often dense pack cellulose installers, and it doesn't take much prompting to get stories all kinds of stories of how the spray foam has failed. You know, and so if we're switching from spray foam to dense pack insulation, we're not taking the jobs away from the installers typically. They're just changing their materials, and we have less hazmat suits on the job site. Foam boards, certainly not as toxic or as big an environmental issue as spray foam, but as Joe is the first to say, foam shrinks, and it expands too. It moves with the environment. You need to have essentially control joints for your foam, and so this is you know, and it's not moving with the construction in the way that the wood construction is necessarily moving. So this poses a challenge. So we're installing something that is imposing a challenge to then overcome. By contrast, if we install control layers that do the job in a truly continuous way, we can hit the high performance goal. So here we have on the right interior air barrier vapor control over the joist that is truly continuous. The fewer the junctures, the better. And on the outside, truly continuous. And I want to say, you know, we believe that you know, the water needs to be dealt with by gravity. We don't want tapes being the waterproofing flashing per se. The weather-resistant barrier here in this case that is waterproof, it's airtight, and it is vapor open, can shed the rainwater very effectively with simple lap joints. They don't even need to be taped. But what we want to tape all the joints for is for our airtightness. So with the weather-resistant barrier on the outside, tape joints, you can actually hit passive house level air tightness and pass your blower door test. But again, to optimize the insulation, optimize the ultimate performance of the building, we want air tightness on the inside, and this is what we see on the right. So continuity is everything. Simplification. This is a great detail from Gregory Laverdera, whose website everyone should go visit. To simplify, here he's taking a Swedish framing, typical framing, and modifying it for the American market. And the long and short of it is he's composing a wall where the internal air barrier is a very simple, straight line. If you don't have that kind of situations, you have sort of these in and outs of the air barrier location, and so it's critical that we address them and make it continuous, and this gives us the success. Sequencing. Step one on the left is to add a bit of air barrier, and then on the right we have the wall being applied perpendicular to it. So you're set up now for continuous air tightness, vapor control, etc. And you're not stopping and starting. So by sequencing properly, you're simplifying and you're ensuring success. And I should note that these photos and the ones before with the continuous air barriers on the outside and in, credit Ed May and his team at Building Tip, and they have a great blog as well, a spectacular blog showing the details and photos from their work in this house that's going up in Wisconsin. I encourage everyone to see it. We also have on our website, 475.com, a Sites We Like page, which I encourage everyone to go take a look, and lots of different building science blogs, project blogs, a lot of things that we're keying into and appreciate very much, and I think you will too. So take a look at that. Want to make connections robust. Buildings move. So this argues to the flexibility, longevity. Too often, sealants dry and brittle and fail over time, and it's particularly when you have a house where the components are moving. So where we're making these connections, so we want membranes that are moving with the building, and particularly at the connections, we want connections that can move and take a good deal of movement and still maintain the air tightness. So here we have a tape adhesive that is quite severely wrenched like an earthquake zone and maintaining its adhesives there and the tension. So another part of the robustness and continuity is to treat carefully dissimilar materials where membranes are coming together, where you have materials that are rough or porous. We have acrylic adhesive. There is acrylic adhesive that will fill the gaps, will not embrittle, will have great strength and stand the test of time. So really, if we're talking about continuity and robustness, we need to address the penetrations, and there can literally be 1,000 of them in a building. We also want to reduce the number of penetrations. So windows are a big one, and too often, if we think 2-part spray foam is problematic, 1-part spray foam, you're sort of guaranteed not to hit the new sort of air tightness levels that all too often we've seen with the blower door and a thermal camera just leaks, if not everywhere, virtually everywhere, certainly to some extent on every window, and completely sort of unpredictable. So it's a real crapshoot. We want to tape our windows in, and this could either be face taping to the frame that's going to be covered by finish on the left, or tape that is on the right, which is taped to the outside of the frame before it's installed, and then back onto the enclosure. There's adhesives actually on both sides of that whitish blue fabric. Gasketing and tape. So all the penetrations that we're talking about, wires penetrations, pipe penetrations, duct penetrations. EPDM gaskets give great flexibility and robustness to those connections. You're not taping to the pipe, you're taping the EPDM gasket to the air control layer. We also say allow room to gasket properly. It's too tempting too often to put the wires or the pipes jam it right into the corner, but like waterproofing from the outside, air tightness is no different. You'd like to have some space there so you can get to it, you can verify it, and if there are leaks, you can fix it. Another option to the EPDM gasketing is just a flexible tape, and there are new highly flexible tapes you can cut into short strips that move quite a lot and maintain the adhesion, the air tightness. Beam penetrations, on the left we see a progression of felt tape felt tapes surrounding the beam penetration, which is then plastered over and making a unified air control layer, or on the right where we have wood sheathing up above or membranes down below. But we have complete sort of approach to all those penetrations. So with all the penetrations, the simplification, the continuity maintained, we want to protect the control layers. And service cavity is in many ways a new concept, but we think a very worthwhile and robust one. And that in service cavity, where you can install horizontal strapping over the air control vapor control layer, you then can run your services on the inside of that control layer, and you thereby minimize the number of penetrations and can just bring the number of penetrations down to a handful. And going forward in the future aids in its robustness and protecting it. You can also add insulation to that service cavity if so needed or warranted. You could put some bats in very simply, adding to the overall performance. On the outside, we protect our control layer with a rain screen. So we have battens there, vertical battens over the rain screen, and then horizontal siding in this case. And the rain screen is just, we could not say enough about it. It keeps the bulk water off of the building. It protects the control layers from the sunlight, and it protects them from general abuse. And as we said earlier, it helps maximize the drying potential to the outside. So really wonderful and an almost essential part of high-performance assembly. So simply in review, the high performance today, the control, water control has always been essential, but we're up to passive house air control. We want active, resilient vapor control, not passive, prophylactic vapor control. We want thermal bridge-free construction. We don't want it to do it for more money, and we want to do it in a way that's sustainable for the occupants, for the workers, the construction workers, and for the planet, and addressing our climate change crisis. We want to be able to achieve it year-round, and we want the results to be predictable and long-lasting. So what are some of the details? Briefly, and I should say I'm just going to flip through a couple of things here, but you should come to our website. We're always putting up more details. We're sharing details from, as we're developing and seeing what's working, what's not, what's more optimized. We're putting details up on our website and sharing them, and hope you can take a look, hope you give us feedback, and we're looking forward to growing an ever larger library covering all climate zones and covering certainly the major sort of building assembly typologies. Many of them, I should say, are sort of evolutions from what we've seen or new ideas. So here we have wall, I-joist wall. So from the outside we have the rain screen, we have a wind-tight, airtight, weather-resistant barrier. So again, maximum diffusion to the outside. We've got the I-joist with dense packed cellulose, managing the water and insulating. And on the inside of the I-joist, we have CDX plywood sheathing, which is our resistant barrier, and our air barrier on the inside, vapor-resistant barrier and vapor variable. And then inside of that is a 2x4 wall, and the 2x4 wall is acting as the structure and acting as the service cavity. So you almost have, it's sort of like the much more natural and active dynamic assembly reinterpretation of a persist wall, perhaps. On the inside, you could have insulation added to the 2x4 service cavity as needed. And then we have a double stud wall enclosure. And this we're showing, for argument's sake, without sheathing on the inside or outside. We have a rain screen on the outside and weather-resistant barrier. Again, the cellulose, dense packed cellulose in the double stud construction. The stud on the inside would be the structural wall again, and then rather than plywood, we have a vapor variable membrane that's acting as the airtight layer as well, and then the service cavity. For the floor, what we're looking for is in sort of the most distilled and simplified version is disengaging it from the ground. So you could have either on piers or a crawl space or an uninsulated cellar. And you've got the exterior wind-tight, airtight, weather-resistant barrier wrapping around the outside, and we have that insulation continuing in the floor I-joist. And then on the inside, we're carefully connecting the interior, the CDX plywood on the interior of the I-joist and the wall to the plywood that's on the floor. And so that plywood is maintaining the interior air barrier on the walls and floor. And the weather-resistant barrier is on the exterior. If you have an insulated cellar with insulation to the outside, we're showing a configuration where the floor joists are actually going out as outriggers to pick up a double stud or I-joist wall construction. In this case, the double stud wall construction, many of the same characteristics. Truss roof, we're looking at a vented roof, again, on top of the weather-resistant barrier, airtight, wind-tight, vapor open, and waterproof, again, and with cellulose in it, not dense pack, but just loose blown. We'd like to fill the cavity all the way up if we could. Why not? And then we have an intelligent membrane on the bottom. Again, addressing the roof. Even though we don't have an asphalt shingle roof here, the intelligent membrane on the roof is really bringing the most robustness and is sort of a preventative measure in that case to prevent wetting and maximize the drying. It's also our airtight layer on the ceiling. Cathedral ceiling, again, showing a vented roof as the more robust above a weather-resistant barrier. You could still have an asphalt shingle roof there and have it be a vapor barrier. And again, all the more reason to have an intelligent membrane that is acting as an air barrier as well to optimize the roof construction, the robustness of it. So those details and more will be up on our website, and we hope to speak with you more about it. I'll say in summary, a more cost-effective, active, robust, and durable enclosure is not only possible without foam, its elimination is practically mandated. And with that, we rest our case, and we look forward to working with you in the future and looking how we can build more sustainably and more robustly without using foam. For more information, you can contact us. My email is ken@475.com, or our website, 475.com, and Twitter. Please follow, and we'll follow back and have the conversation going. We look forward to it. Thank you very much.